Math 2414, section 9.2, calculus with parametric curves. Video 9 of 9, example 5. As not so subtly suggested at the end of the previous video, this last one's going to be finding the arc length of one arch of a cycloid. Remember, this is the shape you get when you start with the circle sitting on the x-axis, tangent at the origin, and you rotate the circle along the x-axis and keep track of that point that was originally at the origin. After one complete revolution, it's back on the ground again. And our question is to see how far that point traveled. Now, there's a couple of ways we can attack this. Number one is to do the problem for this whole arch. But number two, based on symmetry, we could probably just go from 0 to pi and double the result. But let's not get too crazy because symmetry is not always an option we can take advantage of. So we'll just set up the problem as is. I've already written not only the parametric equations for a cycloid of a circle of radius r, but the derivatives of them since we've seen them already. Because we're going to need those derivatives when we set up the arc length. The arc length is going to be from, remember the values of the parameter were 0 to 2 pi for one complete arch. 0 to 2 pi, square root of the sum of the squares of the derivatives. The derivative of the x term is r times 1 minus cosine theta. So all that's going to get squared. The derivative of the y term is r sine theta, so that's going to get squared. And then d theta. All right, let's think about how to be efficient with this. Each factor in each parenthesis is going to get squared, so the r is going to get squared on both of them. That will be a common factor across the addition sign, which means we can factor out the r squared. Square roots distribute across multiplication. So when we write these radicand as r squared times something, we can square root just the r squared, make it an r. And because it's a constant relative to theta, we can put it in front of the integral. So without much algebraic documentation, if you will, we'll go ahead and do all that with the r. Square it, factor it out, square root it, move it out. So we can focus on the rest of it. Now, under the square root, we'd be left with 1 minus cosine in parentheses squared. We could write that twice and FOIL it out, get 1 minus cosine 2 theta plus cosine squared theta. Remember, we already factored out the r's. That leaves us with just sine squared over here. I see something we can take advantage of. Anytime you see 1 squared, trig function, cosine squared or sine squared, you should hope the other one appears. Cosine squared plus sine squared is 1. And there's another one over here. They're both positive, I can combine them, and I can get a 2. So we have the r times the integral from 0 to 2 pi of the square root of 2 minus 2 cosine theta, d theta. It's at this point where it looks like we might be at an impasse. However, there's a trick we can pull, and I'm trying to figure out the easiest way to bring this trick up without just saying, isn't it obvious? What's the trick we can pull? Well, I can't think of a natural way to show you what I'm about to show you. So I'm just going to pull off a trick. I'm going to factor a 4 out of the radicand. I know they don't have a 4 in common. They have a 2 in common. But the reason I'm going to factor out a 4 isn't just because I can square root the 4. It's because of what's going to be left. How do you factor out a number that's not there? And the answer is you divide by it. Think of it this way. If I put both of these over 4, 2/4 minus 2/4 cosine theta, then redistributed the 4, wouldn't all the 4's cancel and take us back here? It would. So that justifies that I can factor out a 4. Truth is, you can always factor out anything you want. If it's not there, just put it underneath. Then when you redistribute, they would cancel anyway. But why 4? What's so special about 4? Well, what's special about 4 is what the 2's become. The 2's become 2/4, which is the same as 1/2. Additionally, I can now split off this 4 since it's a factor in its own square root the 4 to get a 2 and put it out front with the r. So let's do that. And then under the square root, we have 1/2 minus 1/2 cosine of theta. D theta. Now, why is that helpful? Where have we seen 1/2 minus 1/2 cosine theta before? Well, we haven't seen precisely that, but we've seen something that looks strikingly similar. Haven't we seen in a power reducing formula something that looks like this? We did. What we saw was sine squared of 2x is equal to 1/2 minus 1/2 cosine of, sine squared of x equals 1/2 minus 1/2 cosine of 2x. So structurally, these things look the same. The only difference is that has just a theta, that has a 2x. The letters are relevant. I could call this thetas instead of x's. The point is, this cosine doesn't have a 2, this one does. So how can we fix that? Well, that's easy. Just let 2x equal theta. That would put a theta here, but what would it put here? Well, 2x equals theta, what does x equal? Theta over 2. That means another version of the power reducing formula is sine squared of theta over 2 equals 1/2 minus 1/2 cosine of theta, which is really helpful because number one, it collapses this binomial into a monomial, and number two, it collapses it into a monomial that's squared and currently living under a square root. So is it a dirty trick to not only pull out the 4 but play this smoke and mirrors game to be able to capitalize on the power reducing formula that has 1/2 minus 1/2 cosine of something? I don't want to say it's a stretch, it sort of is, but the further along you go in calculus classes, the more you have to be broad-minded about grabbing things from other courses, trigonometry, algebra, geometry, wherever, and not be afraid to say, well, I've seen something that looks like this before, let me see if I can take advantage of it. And because I've seen something that looks like that before, I can take advantage of it and replace the radicand under the square root with sine squared of theta over 2. You can't be afraid to take previous knowledge and adapt it to a current situation. You can't be afraid to look at things from a reverse perspective. Normally it's sine squared equals that. Well, let me look at it in reverse and adapt it to what I need now. But if you can get to this juncture, you're practically home free. Because again, the square root cancels the square. Why did I put a 4 here? Oh, because I was talking 4s and they should all be 2 pi's. Wondering how I got there. But I digress. The square root cancels the square. Well, it'll cancel the square as long as sine is positive. And I know what you're thinking, sine isn't always positive over 0 to 2 pi because sine in its own right is this number, 0 to 2 pi. But it's a theta over 2, which means it takes twice as long for it to complete one period. So it would take 4 pi for it to complete one period if we put it over 2. In other words, we're cutting our thetas in half, so it takes twice as long to run the whole course. So this trig function is positive from 0 to 2 pi. But even if you didn't catch that, you would be okay. Antiderivative of this technically requires a u sub. Antiderivative of sine is negative cosine. Theta over 2. But if we were to take the derivative of this, so we would pick up an extra 1/2. And we don't want the 1/2, so we need a 2 to balance it. It's your pretty standard u substitution without doing it, where your u substitution's derivative is a constant. So you balance the integrand with the reciprocal of the constant. In this case, the derivative of the inside is 1/2, so I'll balance it with its reciprocal, which is 2. This is going from 0 to 2 pi. Let's clean this up a little bit. Negative 4r cosine theta over 2 from 0 to 2 pi. And in cleaning it up, I made it kind of messy. All right, let's put in pi. negative 4r cosine of 2 pi over, let's put in 2 pi. 2 pi over 2, which is pi, minus negative 4r cosine of 0 over 2, which is 0. Cosine of pi, cosine on the left side of the unit circle is negative 1. This is negative 1 times 4r, which is negative 1 times negative 4r is 4r, minus, well, minus minus is a plus. Cosine of 0 is 1. 1 times 4r is 4r. Looks like it's 8r. Which means this point, upon one complete revolution, travels 8 radii all the way around. That was crazy. Actually, the setup wasn't that bad. The setup of the integral was pretty straightforward. The cleanup, a little bit of trig identity, getting here, not a problem. But I'll admit, pulling off the let me factor out a 4 and then take advantage of that trick, that power reducing identity in a way that's unconventional, it's not intuitive. Things like that take time and experience and exposure to them. The more you see things like that, the more they start becoming part of your arsenal of moves that you can make. I wasn't kidding when I said most students who take calculus struggle because of the algebra and the trigonometry. Put on top of that, being able to look at things from perspectives that you don't normally look at. Oh, I'm going to turn this into this, and that's how we always do math. Pfft, please. Math is use any information you know to get the answer that you want. And it's not just about getting the answers, but figuring out how to get from the beginning to the end. In other words, how to solve problems. I'll get off the soapbox now because I imagine this video is already kind of long, and but it's the last video, so hooray for that.